A very useful problem-solving technique especially for circuits that are a little more complicated is what's called Kirchhoff's rules, where you just can't directly apply Ohm's law all the time. So we're going to look at that for a few minutes. It consists of two basic ideas, namely the point rule, which just says that the total currents entering a junction is equal to the total currents, I bet you could fill in the blank, leaving, yes. And that's simply a consequence of the fact that if it wasn't true, then we would have a buildup at a certain point in a circuit, and you can't have a buildup of charge, because that's what current is, the flow of charge. And you would end up with a disastrous situation and a resulting lightning bolt, either charge entering or leaving that point of buildup or lack of a certain kind of charge. All right, so if we have current 1 entering a junction, and we have current 2 leaving the junction, then this third branch better be consistent with all entering is all leaving. If I1 flows in, and I2 flows out, then what goes here has got to be the difference between the two. What if I1 is more than I2? Then it's I1 minus I2 that has to go this way. That's as simple as that. I mean, if I2 ends up being, you can have any combination and have this work. I2 could be more than I1. That just means that I1 minus 2 is negative, in which case there's current entering here as well to contribute to the larger I2. Make sense? So the sum of the currents in to a junction is the sum of the currents out of that same junction. That is the point rule. So in addition to the point rule, we have what's called the loop rule. And this simply says that the total voltage that rises in a circuit is equal to the total voltage that drops. Or the voltage rises is equal to the voltage drops. Namely, the sum of the rises across each element is the sum of the drops across each element. Some elements will be a rise, some will be a drop. So we'll go through this. Another way to say this is that all the rises equals all the drops is that as we navigate a circuit, the total voltages added up algebraically equals 0. Let's do an example. This is actually a very simple example. Simple enough that we don't even really need Kirchhoff's rules. But I'm going to use it to illustrate in simple form how we do this, as a first pass at least. And I'll explain basically the method, okay, the cookbook method over here for doing this analysis. First, you have to pick a loop direction. Well, we only have one loop here. So we have one loop. We can either analyze it clockwise or we could go counterclockwise. I'm going to go clockwise. I have a clockwise propensity or bias, and so that's what I'm going to do right now, but it's not that important. Then we're going to pick a starting point. I am going to, if you look at this, and you had to guess at what point I'm going to start with, you'd probably guess A. Okay, again, not important, but that's where I'm going to start. And I'm going to work my way clockwise around the circuit and write the voltage across each element and whether it's a rise or a drop. So I'm going to write the equation in the direction chosen. The plus and minus signs are very important. And we're going to have to write as many of these equations as there are loops. So since I only have one loop, there's only going to be one equation. All right. And the sum of the v's should equal 0 as I go around. So here we go. Clockwise, V1. As I go from negative to positive, it's a rise, negative to positive. This up here is a greater voltage by V1 than it is on the back side. So it's a voltage rise. So I just wrote V1. Now I encounter R1. Now the voltage across the resistance is I times R. So this is going to be IR1. But is it a rise or a drop? We've already seen in our introductory analysis that as we consider navigating, so to speak, across a resistor, the energy of the charges diminishes. So the voltage is higher, or the energy of the charge on this side is higher than the energy of the charge on the other side. So it's going to be a voltage drop, which means that the voltage is negative as we navigate across there. It's a drop in voltage. So minus IR1. Now, we have plus to minus. As we navigate in this direction across the second battery, which makes this circuit perhaps just slightly less trivial than a just simple series circuit with a resistor or a combination of resistors and a battery. It's two batteries. And they happen to be kind of fighting each other, if you'll notice. The positives are connected together. I don't know which voltage is bigger, so I don't know which one wins. But that information isn't important for the time being. But as we go from plus to minus, we have a drop. So is that minus V2 or plus V2? That's right, it's minus V2. And then we encounter, and realize, of course, I'm talking about as though the circuit or the charges in the circuit are encountering these things sequentially, but you know they're not. It's all simultaneous. Nevertheless, in our model and the subsequent analysis, we can consider it as such. Well, and in any case, when we encounter a circuit element, we can decide sequentially what's happening at each of these, even though they are happening simultaneously. Thank you very much. So R2, drop or rise. That's right, it's a drop. So minus IR2, likewise minus IR3. And we've just navigated around back to point A. So all these things together add up to, here's the answer, 0. All right. So there we go. Now I'm going to reconfigure this just a little bit. We have to solve the equation, so let's do it. V1 minus V2, and then we have the same current going through each of these resistances, and there's a minus in front of each one. So minus I times R1 plus R2 plus R3 equals 0. And so now we're ready to solve the problem. I times R1 plus R2 plus R3, I basically put this on one side, equals V1 minus V2. So we can solve for the current, simple ratio of the V's over the R's. Now if you look at this, you realize, wait a minute, couldn't I have just done this in my head? I mean, using Ohm's law? The answer is yes. What's the current in the circuit? Total voltage over total resistance, series circuit. So V1 minus V2, because it's opposing, divided by R, and it's R1 plus R2 plus R3. We could have had this written down in just a few seconds. But I went through all this detail because in the next video, we are going to look at a circuit that requires Kirchhoff's analysis. It's not quite so trivial. In any case, if this turns out to be negative, we know that V2 then is just bigger than V1. And which way is the current really going to go then? If this voltage is more than this voltage, the current is really going counterclockwise. So it's just the opposite of the chosen direction. And that's real easy to see just by the sign of the answer. And now let's progress to the next little lesson where we solve a more complicated circuit that requires Kirchhoff's laws, and we're not able to do it only with Ohm's law.